have our first unit of Unit 7 is just our introduction to parametrics. So in looking at parametrics, what we're trying to do in general, instead of giving an x, y coordinate, like say y equals 2x, we would choose a set value or a series of values for x. We would plug them into the equation y equals 2x, and we would get a y value. And then from that set of x, y coordinates, we would plot it. So we're doing the same thing again, but in parametrics, rather than saying x is x and y is whatever happens to x, we allow each variable x and y to be dependent on a third variable t. And a good example, like a real life example, where does this kind of come into play? It has to do with, the most common example has to do with projectile motion. And so if you've been in physics and you've had, a catapult unit or any kind of unit relating to a projectile motion, you could have used this method. And how that works is in projectile motion, if you look at kind of a graph of the position of an object that has been thrown, what you can see is that over time, the distance or the position in the x direction is changing, but it's changing with respect to time. And in the same regard, the height of which the object, let's say you throw a ball, the height of the ball is changing, but it's also changing with respect to that same variable time. And so we look at that from a real life perspective. We would want to know the position of x, like say for example here, the position in the x direction is dependent on t, and so is the y position. Its position is with respect to t. But we're not going to get that in-depth first. The first thing we're going to do is we're going to consider plotting a set of points. So instead of choosing x, plugging it into the equation, getting a y, and then getting an xy coordinate, we're going to do the same thing, except instead of putting in x's and y's, we're going to choose a set of variable values for t. So let me get my pen. So what I'm going to look at here is plugging in t for the x equation and the same variable value, -2, for the y equation. And when we do that, you plug this in, -2 squared plus 5, that's 9. And when you do the same thing for y, you get -2. Now that we have the x solved for t and the y solved for t, we see that we have a coordinate. We have a coordinate 9, -2. And then we can go over here and plot this point. So 3, 4, 5, -2. So there's the point. And we can continue to do this. We plug in -1 squared plus 5 is 6. And the same thing over here, that's just -1. In fact, you can see that y is just equal to t. And if we plug in the x equation and solve t, we get 5 and 6 and then 9 again. So we get all these coordinates. And if we plot all of these coordinates, they look something like this. So 9 was 2, 8, 7, 6 was 1, 5 was 0, 6 was 1, 9 was 2. We get this graph. So what we see, or what we see the start of, is kind of this sideways parabola. So you just fill it in and get your answer. So that's really all you're going to do in example 1 and example 2. Example 2, if you plug them in, Again, it's just as simple as taking -2 in for t for both the equations. So give me a second here. I'm going to pause the video just so we can save some time, and I'll fill this table in. So just like example 1, we have all of our data put in for our t values, but this time you can see the graph looks like this on the right. So again, all we're trying to do is plot the few points and then estimate the graph. If we look at example 3, 3 is going to be similar, so I'm going to skip it for now. I'll fill it in later, but we're going to get to a point where plotting the points is either not enough information or it's a little complicated, kind of like in our polar graphing. Sometimes a few points isn't enough to see what the graph really looks like. So we're going to move on to example 4. And in example 4, what we're trying to do is basically graph the path that a bug is going to take. And then we're going to compare that to the path of a second bug and see which one wins a race. Because, you know, everyone races bugs in their spare time. So when we look at this, the information given says that the trek, or the race, is 70 inches long. So that's kind of our parameters. We're looking for critical information. So bug 1 is going to go 70 inches. Bug 2 will also travel 70 inches. The difference is bug 1 starts at time 0 and goes at 12 inches per hour. So question A, given that t represents bug 1's time, what formula can we represent the distance? And from up here, you know, we have this distance equation. Distance is just how fast are you going and how long did you go at that rate. And so distance of bug 1 is rate times time. The rate we are given is 12 inches per hour. But we don't know how long it's going to take the bug to get 70 inches, so we just leave that time as the variable t. Then we look at bug 2. It says bug 2 is going to travel at 18 inches per hour. And again, we don't know how long it'll take bug 2 to get 70 inches, so we leave the variable t. But the other piece is that the bug actually leaves, bug 2 leaves an hour after bug 1. So what we really need to do is say t minus 1, because if we set it times 0, you know, bug 1 gets to start. After 1 hour, bug 1 has traveled 12 inches. But see, after 1 hour, we can't let bug 2 have gone any distance. So if we say t minus 1, that allows us to account for that 1 hour head start that bug 1 gets. So now it says, which bug do you think will win the race and why? That is based on no calculations, no graphing, no anything. It's just take a second. You're supposed to think about how could you determine which bug would win a race that is 70 inches from the start. So I would take a second, pause the video, and consider how would you determine which bug wins the race. So hopefully you paused the video and you determined that it was, in fact, bug 2 that wins the race. A couple ways to do it. I'll just cover one. But if you look at, as time goes, you just incrementally, if you create a table at 1 hour, bug 1 is 12 inches, bug 2 is 0. After 2 hours, bug 1 is gone 24 inches. Bug 2, after 1 hour, after 2 hours is 18. At 3 hours, 3 is this critical point, because at 3 hours you've gone 12, 24, so you've gone 36 inches for bug 1. And in 3 hours, you look at the same thing for bug 2, it's 0 after 1 hour, 18 after 2, and then 36 after 3. So here's what happened. After 3 hours, they are neck and neck. So bug 1's going along, bug 2 waited a little bit, but then finally they're able to meet up. After 3 hours, they've each gone 36 inches. they need to go 70. But at 3 hours and 36 inches, they're neck and neck. So any time that passes after that, we can determine that bug 2 is going to be traveling faster than bug 1. So we don't know how long it'll take to get to the end. We just know that after 36 inches, any race after that, bug 2 is going to be in the lead. And that's how I determined that bug 2 won the race. We will then go through and separate video, because that's enough for now. Separate video, I'm going to show you all the graphing calculator work for this problem. Because in this case, we can actually use graphing calculators to answer all of the following questions. So I'll pause here. We'll pick up in part 2.